Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from University of Delhi, Department of Physics and Astrophysics. Today we are going to discuss about the module Transducers Part 4 from the paper Measurements and the Instrumentation. In this module, we will study about transducers and how they are used in measuring various external forces. Our objectives are to develop understanding about the transducers, look into their instrumentation design, and its functioning based on the application. In the current module, we will study about load cell and piezoelectric transducers. Transducers were developed for converting a non-electrical quantity into an electrical signal. This electrical signal is further processed by some electrical and electronic circuit that supplies output to a device for indication or for recording purpose. Sometimes a transducer is used as a primary transducer where input signal is sensed directly, and in some cases transducer is used as a secondary transducer. Here a detector first senses an input signal and its output is supplied to secondary transducer as an input signal. In previous modules, we studied about LVDT, inductive and capacitive transducers. In this module, we will study about other types of transducers like load cell and piezoelectric transducer. Load cell. A load cell is also known as a pressure cell. It is a device that can convert weight, that is pressure, or mechanical force into electrical signal. It is widely used for measuring dynamic and static forces. The heart of this device is load, that is weight, force or pressure receiving element, which is an elastic element having a high tensile strength. This element is bonded to strain gauge bridge network. The output of the load cell is derived from the deformation of the elastic element made of homogeneous material like steel alloys. One should carefully select the material and its structural configuration so that one can have a linear relationship between the dimensional change and the quantity, that is force, under measurement. A desirable material should have following properties. 1. A fairly large elastic strain limit with a linear strain relationship, say up to 5000 microstrains. Second, repeated overloading should produce low strain hysteresis, that is less than 2 microstrain. Third, very low creep of less than 5 microstrain over long period of loading. And finally, very low plastic flow due to strain. Based on the design of the load cell element, one can have three different configurations. First is column, second is cantilevered bending beam, and third is shear element. Let us study about these configurations one by one. First is column. Figure 1 illustrates the typical design of the columnar type load cell. Such columnar type cells are usually employed in load cell having capacity of 2000, 200 and 250 kg or more. It has two strain gauges called active gauge that are bonded axially. The other two additional gauges are called Poisson gauges and are mounted 90° to axially positioned gauges. The load cell shown in the figure 1 is used only under compression. It has a fitting at the bottom of the base for attachment to the support structure with a load receiving button on the top. During the construction of the load cell receiving element is shrunk fit into the base in a compression type load cell. The lowermost section of the load cell housing is also known as can, which is welded onto a base structure. On the top of the lower can, a diaphragm is welded to the edge of the can and the center column. The upper can is welded to the connection between the lower can and the diaphragm. This completes outer shell of the load cell structure. Finally, the upper lip of the top diaphragm and the central column is welded to the top diaphragm. This seals the inner portion of the load cell, which makes it impervious to gases and the moisture. All the wires from the strain gauge are carried out through a glass to metal seal located in the lower can wall and are connected to the external cable. Second is bending beams. Bending beams type load cell are used for measuring forces and weights below 225 kg. There are few variations in the design, but most common one is dually guided cantilever beam as shown in figure 2. It has 4 strain gauges that are mounted at the corner of a stabilized triangle. When load is applied to the free end of this dual guided cantilever beam, the strain gauge bonded to the element undergo resistive change. This change is proportional to the forces or the load applied. In such type of cantilever beam configurations, the two gauges experience tension and two compression. 3. Shear element configuration. In this configuration, one can have 4 or 8 gauges bonded to specifically designed element and is wired to form a Wheatstone bridge. A centrally loaded shear beam configuration is shown in figure 3. The strain gauges are used in this design differ from those used in columnar and dual guided cantilever design. The strain gauges are designed in such a way that they get activated when they are placed under a shear force. Such elements have an advantage of having higher capacities in smaller size and have low sensitivity to side load error, that is, when load is not placed in proper orientation. The selection of a load for a particular application depends on the following factors. 1. Required accuracy. 2. Scaling capacity. 3. Type of loading tensile. 4. Number of cells required. 5. Loading conditions. 6. Environment. 7. Space available. 8. Desired output characteristics. Piezoelectric transducers. The word piezo is derived from a Greek word piezon, which means to squeeze or press. Certain crystalline and ceramic material can generate a potential difference across the opposing faces of the material when subjected to external mechanical force. Such type of materials are piezoelectric materials, and this phenomena is called piezoelectric effect. This effect is also reversible, that is, on applying potential across the opposing faces of the material, one can get changes in the physical dimension of the material. This principle of electromechanical energy conversion is used for developing energy conversion transducers. The transducer with mechanical input and electrical output are used for measuring dynamic pressure, force, shock, or vibratory motion. Piezoelectric effect can only be observed in crystals having symmetrical distribution of charge due to relative displacement of positive and negative charges. Within the lattice, one can observe contraction or expansion of the material. This displacement of internal charge produces potential difference across the fitted electrode. This is illustrated in figure 4. Here, electrodes are placed on the opposing faces of the crystal, where the output voltages are collected for measuring an external force or pressure. To better understand the piezoelectric properties of the transducing element in piezoelectric transducer, let us consider a case of quartz crystal. Figure 5 illustrates how opposing sides of the crystal get charged with application of external mechanical force. Under no load condition, positive and negative charges are arranged in the center of the equisided triangular form. The two opposing charges at the center point become neutral, and no potential difference gets developed across the opposing face of the crystal. With the application of the external force F, ions within the crystal get displaced within the structure and equilateral triangles get deformed. This deformation of crystal lattice is shown in the figure 5b. In case of application of tensile force, potential of opposite polarity is developed across the crystalline face adjacent to electrodes. Similarly, when piezoelectric material is under the influence of external electric field, crystal may contract or expand depending upon the polarity of the field applied. The polarity and the magnitude of the induced surface charge is proportional to the direction and the magnitude of the external applied force. Therefore, Q is equals to D into F. This is equation 1, where D is the crystal charge sensitivity in coulombs per Newton, which is constant for any given crystal. The force F brings a change in the thickness of the crystal by delta T in meters, where F is equals to A into E divided by small t into delta T newtons. This is equation 2, where A is the area of crystal in meter square, E is the Young's modulus of elasticity, and T is the thickness of the crystal. The charge at the electrodes give rise to the output voltage V out and is given by the following equation. V out is equals to Q divided by Cc. This is equation 3, where Cc is the capacitance in between the electrodes of the crystal. As capacitance is given by Cc is equals to absolute permittivity multiplied by relative permittivity into A divided by T. This is equation 4, where A is the area of the crystal in meter square, T is the thickness of the crystal, and an epsilon R is the relative permittivity. Therefore, by solving and rearranging above equations, we get V out is equals to Q by Cc. This is equals to D into F divided by absolute permittivity into relative permittivity into A by T. This is further equal to D divided by epsilon naught into epsilon R into F into T divided by A. This is equals to G P T. This is equation 5, where G is equals to D divided by absolute and relative permittivity and is the crystal voltage sensitivity in V meter per Newton, which is constant for the given crystal cut, and P is equals to F by A is the pressure in pascals applied to the crystal. Above expressions can also be represented as G is equals to V out divided by T. This is further divided by P. This becomes equals to electric field divided by stress applied to the crystal. This is equation 6. Merits. Piezoelectric transducers are small in size and light. They are self-generating, that is, they do not need external power source. They operate over a wide range of temperature. For quartz, temperature range is of -200 to +300 degrees centigrade, where ceramic device is its limited to +100 degree centigrade. Such systems have quite large outputs. For example, a quartz crystal of dimension 2.5 mm thickness can have sensitivity up to 120 millivolt per kilopascals, and with crystals having an area of 1000 millimeter square, the sensitivity is of 125 volts per kilonewton. Merits. Their output voltage generally gets affected by temperature variation of the crystals. When a transducer is under constant deflection, it develops voltage across its terminals and slowly leaks off through its terminals. This decay of charge is very slow due to high leakage resistance of 10 raised to power 11 ohms. However, this charge leakage is very rapid when a voltage measuring device is connected across its terminals. This prevents measurement of any static displacement of the measurand. In commercial systems, quartz element of high leakage resistance is used, and input amplifiers of high impedance of 10 raised to power 14 ohms slow down the leakage, allowing the measurement of static displacements. Applications of piezoelectric transducers. First, these transducers are mainly employed for estimating forces and pressure. Due to their simple and robust construction, they are used for measuring forces over a wide range, that is, from 1 Newton to 200 Newton, having a linearity of ±1%. Second, piezoelectric transducers due to their frequency response are mainly used in high-frequency accelerometers. In operation, their output voltage is typically of the order of 1 to 300 millivolt per gram of acceleration. Quartz crystals can also be used as mass to frequency converter. A crystal controlled by electronic oscillator has a thin quartz plate. The frequency of electrical oscillations depend on the natural frequency of mechanical oscillation of the plate. Because of their rugged design and configuration, they are employed for collecting data under challenging conditions. They are used in ballistics, blast, internal combustions, fuel injection, flow instabilities, high intensity sound hydraulics, or pneumatic pulsations in connection with problems associated with guns, shock tubes, closed bombs, rocket motors, internal combustion engines, pumps, compressors, pipelines, and oil exploration imploders. So, students, let us summarize what we have learned in this module. In this module, we studied about transducers and how they are used in measuring various external forces. In the current module, we studied about the load cell and piezoelectric transducer. Our objective was to develop an understanding about the transducer and look into the instrumental design and its functioning based on the application. One should note that all transducer design are based on the quantity to be measured. Depending on the application and objectives of the measurement, one should select a transducer that is most suitable for that investigation.